Welcome to the Consulting Specifying Engineer webcast, the ABCs of VRF system design for K-12 schools, sponsored by Trane. I'm your moderator, Amara Rozgis, and I'm happy to be here today on behalf of Consulting Specifying Engineer and CFE Media and Technology. Here's a little bit of information about today's webcast. If you're experiencing issues with your slides or with the audio, please click on the Refresh Media button directly under the presenter's photo. You can control the volume of this webcast by controlling the volume on your own device or by changing the volume on the webcast platform. If you're having technical problems with the audio or the slide presentation, please click on the question mark at the top right corner of your screen to access a list of system checks to try before contacting an online technician. If you do need a technician, please type a message in the Ask a Question box and someone will get to you as quickly as possible. Individual technical questions will be answered in the Answered Questions box. Please type a question for our speakers in the Ask a Question box on the left side of your screen. The live Q&A session will be in about 45 minutes. Please send your questions at any time during this presentation. Today's webcast is being recorded, and you'll receive an email in about a week with a link to the on-demand webcast. To download a certificate of completion and a PDF of this presentation, please use the Event Resources tab on the left side of your screen. Those documents will also be available with the on-demand version of today's event. All right, well, I'm excited to start the presentation with today's presenters, Mohammed Hassan, Ryan Flynn, and Scott Huffmaster. Mohammed leads Trane's Strategic Accounts VRF team. He started with Trane in the New England office, where he sharpened his VRF skills and expertise by supporting engineers with VRF design and application support. Today, he works directly with Trane's national sales team, as well as customers, to provide VRF and ductless design assistance, application support, and post-sale fulfillment. Mohammed is passionate about the future of sustainable buildings, decarbonization, and renewable energy policy. As a Virginia Tech grad, he received his bachelor's in aerospace engineering and is currently working on his MBA. Ryan is a senior level engineer with experience in HVAC system design for a wide range of projects, including office fit-outs, shell and core, high-rises, laboratory facilities, airport terminals, and he specializes in K-12 educational facilities. He has been designing VRF and refrigerant systems for the past 15 years and offers firsthand knowledge of applications. Current projects include an all-electric 400,000 square foot high school in construction and another 200,000 square foot zero net energy high school in design. Ryan has a bachelor's degree in mechanical engineering from Wentworth Institute of Technology and holds a PE license in Massachusetts. As the Healthy Spaces sales leader at Trane Technologies, Scott is responsible for leading Trane's indoor environmental quality efforts for the United States and Canada. This includes Trane's WellSphere initiative, a holistic approach to building wellness that cultivates healthier indoor spaces by enhancing air quality, lighting, and acoustics. Scott helps customers achieve customized, healthy spaces while aligning with Trane's strategic mission and objectives. Scott holds a bachelor's degree in electrical engineering from the University of Texas. All right, gentlemen, let's get started.
Thank you so much, Amara. I just want to start by thanking everybody for joining us today. We'll be talking about the application of VRF systems for K-12 environments with specific design considerations. We'll touch on some example projects and indoor environment quality concerns, followed by a brief overview of Trane's connected service offering for VRF systems. We'll also have a small Q&A at the end, as previously mentioned. So just to set the stage, in the various stimulus plans that have been passed, there's roughly $180 billion in federal funding, while a significant amount of that money is focused on safe reopening of the school system. The local school systems retain a high degree of autonomy on how to spend that money. So inevitably, some of that money will find its way into capital expenditure projects. Furthermore, the municipal bond market remains healthy, and VRF as a product segment within the larger industries is increasingly popular and is experiencing significant growth. VRF is a great solution for K through 12, and we'll be talking more today about why. And with that, I will turn this over to my co-presenter, Ryan, to talk about some of the driving factors for choice of VRF systems.
Thank you, Mohammed. So why do we use VRF in K through 12 schools? Well, VRF technology delivers occupant selected temperatures for multiple zones, and it's ideal for buildings with diverse occupancy. Also delivers simultaneous heating and cooling. Can be easily customized and tailored to comfort all areas, from offices to classrooms to lunchrooms. It can even provide spot solutions for challenging areas like data centers and kitchens. Probably the number one reason, efficiency. VRF heat recovery systems provide simultaneous heating and cooling, and it can respond to rapid changes in building load during periods of heavy demand. And also, no central heating or cooling systems are needed. It's a good primary or supplemental solution for zero net energy buildings or electric buildings. Nowadays, what we're seeing in the Northeast is we're seeing the desire for a lot of zero net energy or electric buildings. You have, one of three options for have electric boilers or some sort of electric heat recovery chillers, or you would have a VRF system. VRF systems are also very efficient with coefficient of performance values anywhere from 2 to 3, depending on the season. Another reason why we like VRF is because the acoustic properties. Low sound levels. These outdoor condensing units, they consist of a propeller fan and either one or multiple compressors inside a insulated cabinet. And also location flexibility. If you have, if you're close to a property line, you can shift these systems away from the on the building, almost anywhere on the roof, or away from these property lines or these sound sensitive areas. Flexibility. It's less intrusive to building architecture, and it takes up less space than traditional air handling systems. It can be standalone or part of a central system. It can be retrofit into existing buildings. It's very flexible in terms of area it can serve. We've done systems as small as maybe 600 square feet and done systems as large as maybe 70,000 square feet. It's a known technology. VRF systems have been around for 20 years, and you probably know a lot of the manufacturers that they might even be the same manufacturers who produce the TV in your living room. Again, outdoor flexibility. We've seen these condensing unit roofs, grade. We've even them in basements of buildings, or in some cases, which we don't necessarily recommend, where people bracket them off of exterior walls. And also, these are they're just very flexible systems to meet the needs of almost any educational facility. Cost effectiveness. It's a competitive product with a lot of good manufacturers to choose from. These units are less weight, smaller footprints, resulting in a lot of the times minimal structural impacts in the building. HVAC zoning. An image of a high school, where in design, one of the initial things we do is we go through zoning of the building. So we look at like spaces, and also how these spaces are being used, and also how they're, when they're occupied. So if you look at this top area, this orange, This is actually the main admin area of a high school. So this consists of open and closed office space, meeting rooms. So this is one area that we usually always pinpoint for VRF systems. And the reason why we do that is because admin staff in a school, they generally work longer during the day, and they don't have as many holidays and vacation days as the normal student population. And we try to divorce this system from any central systems to allow the VRF system just to be able to operate without having to turn on your large chillers back at your mechanical rooms. So that way it can operate almost independently of the rest of the building. I'm going to kick it back to Mohammed, and he's going to tell you about K through 12 VRF system design considerations and best practices.
Thanks, Ryan. Before we start and really do a deep dive, I'd like to conduct a small poll. How often, and I'd like to ask the audience, how often do you suggest VRF as a solution to your clients for K through 12 projects? We're not seeing, so we're finally starting to see some results coming from the proposal, and roughly 50% of the audience seems to suggest VRF systems as a solution to their clients, and that seems to be about right in terms of how popular these systems have become. So, broadly speaking, there are two types of VRF systems. There's heat pump and there's heat recovery. Heat pump is typically straight heating or cooling. That is, all of the indoor units are in the same thermal mode. Heat recovery has an additional component called the branch box. The branch box has heat exchangers, solenoids, and controls that are built into it to allow simultaneous heating and cooling. That's become a hallmark of VRF systems. It also allows the system to direct refrigerant into the different zones that it's needed and allow thermal exchange between different zones in the building. An additional quality that I would like to mention is that while air source systems are more popular within the industry, water source systems are becoming increasingly popular, and we also have heat recovery available within water source systems. They're a great choice for geothermal applications, maybe campuses with existing condenser loops, and if you have large water source heat pump replacements, just to name a few applications. So what drives the choice between heat pump and heat recovery? And it comes down to a few large considerations, right? So does your climate zone have shoulder seasons? If you're in Arizona or Florida, where cooling is going to be a large percentage of your load for a significant portion of the year, then simultaneous heating and cooling is probably not needed. And it also might come down to the space that you're working with. Is it a gym area in a K through 12 school, or is it an admin area with some interior zones and some exterior zones, which might experience different thermal conditions in those shoulder seasons? Additionally, what are the types of loads on your system? Does your system have large block loads? We typically get asked a lot about putting IT rooms or other spaces with large block loads onto heat recovery systems. It's important to remember that heat recovery on a VRF system is typically suitable only for comfort applications. The condensing unit still has a cooling main or a heating main mode. So we size the system for full load. At part load, the system can be in cooling or heating main. And so the only source of refrigerant for the IT room or the gym becomes the recovered refrigerant from the other zones. And so as a result, in part load, the non-dominant mode can suffer. It's also important to remember that heat recovery systems, as previously mentioned, do have additional components. The branch box typically does require condensate removal and power, so it can be an additional cost on the project. ASHA 15 and 34, I see a lot of questions in the chat. about how to navigate around the ASHRAE 15 and 34 regulations. For the uninitiated, standard 15 and 34 govern refrigerant in occupied spaces. R410A is a group A1 refrigerant. That's the standard for VRF systems in the industry. The term of concern in the code is the occupied space. It's important to remember that the occupied space does include the plenum space and the supply and the return ductwork. Typically, the ASHRAE 15 calculation is done by the engineer of record and facilitated by the manufacturer. So the manufacturers do have proprietary software that calculate the refrigerant charge for each of the circuits. So the minimum applicable volume in an ASHRAE 15 calculation is the smallest volume in which the entire charge of the system could be dumped, and the concentration of the refrigerant could still be above the RCL limit for R410A, and thus be safe for human presence. If a space is too small, we typically recommend increasing the room volume through permanent openings, louvers, transfer grills, door undercuts, things like that. We also see a lot of times, especially in K through 12 applications, where the indoor unit is actually outside of the space and a ducted style indoor unit's being used, and the air is being delivered through supply and return ductwork. We also, if you're in a very tight application and you can't get around it, we also recommend using, instead of a single 20-ton system, we recommend using smaller circuits. So break that 20-ton system into two 10-ton systems in order to get your refrigerant concentration below the minimum applicable volume. Ventilation is a big topic around VRF systems. Typically, raw outside air can be delivered directly to the fan coils, but this does require MERV 8 filtration downstream of the cooling coil, because this does result in latent work being done at the cooling coil. It's important to remember that especially the ductless style of indoor units are static neutral. That is, that they will not pull in any outside air. So booster fans are typically required for this kind of application. It's also important to remember that there are frost safeties on these indoor units. So, if it's very cold outside, it's 0 degrees outside in Boston, and, you're delivering 50 to 80 CFM of air to the indoor unit, even that small quantity can push the mixed air temperature below the frost safety on extreme days. And so it's important to be mindful of the frost safety. The decoupled outside air, this typically means separating the latent and the sensible load. So the sensible load is done at the VRF terminal unit in the space, and then the latent load is taken care of at an outside air machine. This typically requires the trend within the industry is becoming DOAS units that are discharging at 45-degree air that serves as a vapor sink upon entering the space to maintain the typical 50% RH standard that's typically followed in the K through 12 space. This air coming off of the outside air unit can typically be ducted directly to the unit or the space, and we prefer no method in this. It just typically depends on what's possible for your building, what's possible for your space, things like that. Since these systems are heat pumps, they do have defrost cycles built into them. Trane Mitsubishi VRF condensing units have segmented coils, so they do maintain 50% heating capacity during the cycle. The table that's shown at the bottom right hand of the picture has a lot of, this is the decision tree for our condensing units on how they decide to go into defrost mode. But broadly speaking, there are three main considerations, which is the ambient temperature, the condensing unit pipe temperature, and the cumulative runtime below 32 degrees. The defrost cycle does last for 12 minutes, but during this, as previously mentioned, you will still have 50% heating capacity during this time. We also have a preheat cycle built into all of our indoor units. What this means is that before the system goes into defrost, it will raise the leaving air temperature on the indoor unit for 3 minutes in order to make sure that during the period of reduced heating, the space temperature and the occupant comfort is not lost too much. It is important to remember that we as a manufacturer get a lot of defrost calls when it's a lot closer to dew point rather than when it's when it's very cold outside, and that's just because there's just more moisture in the air at that temperature, and it just freezes more on the condensing coil. So as Ryan previously mentioned, there is a larger electrification push within the construction industry, and which is pushing us for broad-based adoption of heat pumps in order to enable grid-scale decarbonization. VRF systems are ideal for this, and that's primarily because they're electrically driven, but they also operate in a wide range of ambient conditions. So we now have condensing units that can run from -31 Fahrenheit in the heating season all the way to 126 Fahrenheit in the cooling season. And so this makes VRF systems very applicable for a wide range of geographical conditions within the country. The flexibility of VRF systems is being further enhanced now by the capability that's being introduced within the industry to make VRF systems interface with traditional airside products. So we're seeing a lot of applications in schools, especially where unit ventilators are being directly connected to VRF systems, and then that takes care of the ventilation and the heating and cooling as well. It is important to know that these AHU kits typically have a minimum entering air temperature around 0 degrees. So in very cold climates, some kind of preheat might be necessary for these units. And with that, I will turn this back on to Ryan so he can go over some examples of actual VRF projects that he's been a part of.
Thank you, Mohammed. Here's actually one project that, or one situation we ran into in the springtime. So as I said before, it seems like a lot of the Northeast is going zero net energy or electric, or trying to electrify their buildings. This was actually a square foot public high school where they were looking at, 88 700 foot deep geothermal wells to be connected to chiller heaters to serve their entire building. Of course, to the tune of $30,000 per well. Of course, it being with a public building and, the budget and the first cost always a major concern. They were looking at, ways to, reduce first cost, but not take too much of a hit on their annual energy usage. So one thing that we thought about and that the VRF system allowed us to do was we were able to reduce the geothermal well field by 30% by mating VRF condensing units with rooftop energy recovery units for that served every space in the building. Now the total building energy did increase, but we're still able to maintain of an EUI below 30, which we thought was pretty good. This is typically, what you'd see with mating a VRF system to an energy recovery unit. In the background, you see a standard AHU energy recovery device inside. In the foreground, you're looking at 4 VRF condensing units. So these condensing units will be tied to the unit through refrigerant piping and have a single heating or cooling coil. Now, this cooling coil can, depending on the size, can do all of your outdoor air conditioning in the summertime and in the winter. And these VRF condensing units are able to operate well below 0 degrees. So it seemed like, we have the energy recovery device that's pre-treating our air, and then sending it through the refrigerant coil for either heating or cooling, depending on whatever the zone or air temperature needs to be in the ductwork. Also can be used for existing buildings. So here, we did this design about 4 or 5 years ago. It was a gut renovation of a 70,000 square foot middle school. So there was an arts building, as you see in the picture, with the angled roof off to the right hand side. So after looking at plans of this building, and you're seeing it had an average of 12 feet floor to floor, very limited roof space, and had a wide diversity of spaces, including office, conference spaces, music practice, art, and actually an auditorium too. And then the owners desired a lot of individual temperature controls for all these small and large spaces. We thought it was tailor-made for VRF. And the VRF system gave us a lot of flexibility because we only had to mount, I think it was at the end of the day, 3 or 4 condensing units on the roof and have that much roof space to use. Also, because there wasn't much ceiling space, it allowed us the flexibility of indoor fan coil units. Anything from, we use ceiling cassette units to ducted ceiling units, console units, and even some other units just exposed underneath the ceiling. And one huge benefit to this too was just by taking this 20,000 square foot building, it allowed us to reduce our central boiler and chiller sizes. So for a lot of reasons like this, it was just a perfect system to use. Now I'm going to hand it over to Scott, and he's going to tell you about VRF systems for indoor air quality considerations.
Thank you, Ryan, and thank you all for joining us today. It's Scott Huffmaster. I'll be talking about IAQ for VRF. Before we dive into this section, I would like to do another poll here and ask the group how comfortable you are implementing recommended IAQ guidelines for VRF systems. This has become top of mind with stimulus dollars coming, as mentioned earlier, from Mohammed. And we'll go over a little bit of how we can meet those recommendations shortly. So I'll give it a minute to get results of the survey. All right, looks like it's coming in about a little less than a third are not very comfortable yet. About half people are still unsure, and some that are becoming more comfortable. Well, good reason to be on today because this is what we'll be talking about. Let's look at how we can get more comfortable when talking about addressing IAQ with VRF. The first piece I'd really like to highlight for the group is when we're talking about IAQ and VRF, a critical tool to achieve those outcomes of a healthier space and improved indoor air quality is your control system. We've got to have the data, and we've got to be able to pull multiple different levers to deliver on an outcome to really deliver on that healthier space. So, looking at mixed systems where you have a DOAS unit separate from your VRF system, obviously you have outdoor condensers separate from your indoor evaporators, and these can be heat pumps, they can be heat recovery. We've got additional monitoring we can do through controls, potentially custom control schemes. A lot of things we can do. If we don't have the control system that's actually tying all that together, then it makes it very difficult or not possible to do. As Mohammed mentioned earlier, as we're actually developing these products and improving the technology, we now actually have the way to tie in some more traditional equipment into our VRF systems. So here you can see things like unit ventilators, alternative fan coils, blower coils, air handling units, split DOAS units, all able to be tied into your VRF system to make it a more comprehensive system versus individual components. So this is a really good integration tool to help deliver on a healthier space. Now, when we talk about a healthier space, Train focuses on 4 different key pillars of IAQ. I'm going to talk a little bit about how each of these impacts VRF here shortly, but the 4 key pillars are dilute, exhaust, contain, and clean. When we talk about these 4 pillars, what I'm showing you here on the screen is how are these things linking with some of the recommendations that we're getting from the CDC for actions that schools should take to improve their indoor environments. This guidance has been provided to CDC from ASHRAE, so there's a really strong linkage there. And again, as you look through each of these, dilution is really focusing on bringing good air in and the right amount of it. Exhaust is focusing on getting that bad air out. Contain is a focus on maintaining the right levels of humidity in the space, so we're not aerosolizing this virus or potentially causing other issues like mold. And then the last one is, how can we clean the air, whether that's through filtration or other technologies. So I'm going to dive into each one of those independently, specific to VRF next. All right, when we talk about addressing dilution with VRF, what we're really talking about there is how are we ventilating the space? Lots of different ways. You've already heard in this presentation of how VRF systems typically can do that. We could be looking at an energy recovery ventilator that can be indoor or outdoor. You could have a packaged DOAS unit. It could be roof mounted. It could be an indoor, or even a split system DOAS unit that you could have tied in through an AHU LEV kit to your VRF system. All different options of how to help ventilate. And when we're looking at ventilation, what we want to ensure that we're achieving with this is at minimum code ventilation. So what is code ventilation? Again, depends on where you are, but ASHRAE standard 62 is typically going to be your code ventilation. Depends on which standard you're at. Thankfully, 2015 and 2018 are very similar. And so you're going to have similar results as to how much outside air you're going to be bringing in for your occupants. When we're addressing the challenges of this pandemic, one of the ASHRAE recommendations has been to disable demand control ventilation. There's also been commentary around considering increasing our outdoor airflow if possible, and potentially running your ventilation system longer than your building occupancy. We call that a pre and post occupancy purge. Initially, that was focused on 2 hours before and 2 hours after occupancy. There's now some flexibility on how to reduce that amount of time depending on your system type. Now, to achieve these dilution recommendations, again, having controls that can really talk to your systems, your ventilation, whether that's a split DOAS with energy recovery, whether that is a distributed system where you can actually duct your outside air directly to the space and make sure that you're providing that code ventilation at all times, or even a VRF system that maybe has a couple of units that aren't VRF. So an example here might be, let's say you have a cafeteria or gymnasium and you've got that on a traditional rooftop VAV system, single zone VAV, something like that. You could have airside economizer going for some of the systems like that. And then again, deliver code ventilation for your traditional VRF systems. When we talk about the next pillar being exhaust, how are we going to ensure that we're getting the bad air out of our building? So one piece of the guidance here is to ensure that our restroom exhaust is operating anytime a building's occupied and during pre and post occupancy purge. Again, if you don't have this tied into your control system, that can become difficult to do. Some buildings we work with have the restroom exhaust tied to a light switch. And so the guidance is basically going to be leaving that on almost all the time. Another piece of the guidance here is let's make sure we don't bring bad air back in. So a lot of these systems are going to use some form of energy recovery, whether that be a plate or it could be a wheel. There is some pretty extensive guidance on if you're using a wheel to make sure you don't have bad air coming back in. So if you are using a system with the wheel, you would want to be aware of that guidance and make sure that we're minimizing re-entry of contaminated air. Next up, I want to address contain. The contain pillar, again, is around focusing on maintaining the right level of humidity. Traditionally, our focus would be on maintaining humidity below 60% RH in most of our facilities. There wasn't traditionally a focus on keeping humidity high enough because usually we were focusing on preventing mold from growing in our buildings, but we weren't really focusing heavily on it being too dry. What we've learned through the pandemic is when the humidity drops too low, that can have a negative impact on our space. And so there's been some additional guidance that where possible, we may consider adding humidification to our designs to keep humidity above 40% RH, thereby preventing an airborne virus from spreading and aerosolizing. So one of the reasons I really like a VRF system for this is not only can we do a really good job of dehumidifying, do that centrally at your DOAS unit, potentially look at handling not just all your outside air, but maybe decouple your entire outside air and your sensible and latent all in that DOAS unit. Remove the latent from your outside air, but also remove that latent heat or that latent load from the space with that DOAS unit. You can do that centrally, and you can really optimize that with the VRF system. If we're looking at adding humidification, that becomes now a new challenge. Traditional systems with a unit per classroom, you could be looking at distributing many different humidifiers throughout a space, which can become obviously expensive and hard to manage. With the DOAS unit being centrally located, now if you need to add humidification mode for a VRF design with some of this latest guidance, you can do that in fewer locations centrally located at your DOAS unit. Again, most of the time you'll only need to add humidity when the outside air and the conditions are requiring that. Being able to do that centrally can be a big cost saver. Prevents you from needing to do things like in-room humidification, which is again part of the guidance, but can be expensive to do. Last but not least, I want to address the clean pillar. So how do we take the bad stuff out of the air? Core recommendation from ASHRAE and CDC is to provide at minimum MERV 13 filters or higher if possible. And then we want to ensure we have air seals. If that's not possible, then we want to look at potentially putting in portable air cleaners in the room, certainly for higher risk areas. We could consider things like retrofitting air handling equipment with suitable air cleaning devices like UV lights or other technologies. And there obviously is commentary that when possible, we want to increase the total airflow supplied to the space so that we get more air flowing through the filter. One of the challenges with the MERV 13 filter approach is if you have a system that reduces the amount of airflow, you lose some of the effectiveness because your clean air delivery rate is going to go down. So we want to look at where possible using controls to increase airflow and keep those filters running. So what does all this mean when we talk about VRF? Again, integrated controls is a big piece of this. Talking about filters. Okay, so you said MERV 13 filters. Well, how does that work for VRF? Well, a lot of times on ductless systems, it may not even be possible to achieve MERV 13. Typically, we'll see ductless systems that could max out around a MERV 11 level, and that's really about all that that unit can do. Now, if we're focusing on this, you could look at ducted units because ducted units are available with MERV 13 or better. When we're looking at adding an in-room portable air cleaner, you might consider an in-room HEPA. One technology we're looking at is a newer technology called dry hydrogen peroxide. I'll hit on that shortly. When you're talking about cleaning the air that's coming to the space, again, we have some recommendations there based on ASHRAE to use things like UVGI or dry hydrogen peroxide. And then the last but not least, making sure you've got enough airflow. Again, with variable multi-speed fans, we can keep those units running longer and keep that air flowing through the filter to actually be cleaning it. So with that, I'm going to dive in just really quickly on some of the portable air cleaner options that we're seeing in the market and why we would recommend those that we recommend. When we look at in-room HEPA, one of the things that we focus on, we know HEPA works. We know that it's going to capture these bad pathogens, and that is a core recommendation of ASHRAE and CDC. One of our challenges with that is how do we design this as something that's going to be sustainable, that's going to be there long term? You can see in this image here, you have a HEPA along the ceiling that is a fixed HEPA performing in the space, but also you can see down on the floor what looks to be a portable HEPA. When we really compare those two, our recommendation is where possible, look at a fixed HEPA. And why would you do this? Certainly that's going to cost more than a portable, but that also means you're not going to be giving up floor space. You're going to make sure you've got something that's going to be working You're going to make sure that it's on when your building's occupied, off when your building's not, or at least on a night setback. You can ensure your sound ratings are correct. That is a big challenge for in-room air filtration, is sound compromises that we are challenged with. So all of these different things are reasons that for Trane, we're traditionally recommending a fixed HEPA if possible. Last but not least, I do want to address the technology that has come to market that Trane has represented since early in 2021, technology from a company called Synexus that provides what's called dry hydrogen peroxide to the space. So this is a technology that's actually going to put something into the air that you're breathing that is at acceptable levels for an occupied space and can be immediately interacting or deactivating an airborne pathogen. That's a really important thing, especially with what we're seeing today with the Delta variant spreads so much faster and so much easier than the original variant. The interest in this technology has gone up immensely. If you have more information or interest in that, I would just suggest look up Synexus dry hydrogen peroxide. But for now, to keep us moving, I am going to pass back to Mohammed, and we're going to talk about connectivity and controls.
Thanks, Scott. So as Scott mentioned, connectivity and controls have become an increasingly important portion of VRF design as the pandemic has progressed. In the past, VRF systems had a reputation for not communicating with traditional BAS systems. So you would have a VRF system that's running independently of the traditional HVAC equipment in the building, and that would typically be the DOAS unit and maybe some ancillary devices. What Trane has done as part of our joint venture over the last few years, we've developed and integrated the Trane Mitsubishi VRF offering into our Tracer SC Plus platform. This allows the end user access to the outdoor unit points, but more importantly, has proprietary analytics built into it that allow remote monitoring and diagnostics for every single piece of equipment on the system. It allows for 3 quarterly checks that are done remotely. A trained technician would run a report on every single piece of equipment and present those in an integrated and easily accessible form. And then one on-site check that would allow the trained technician to walk simply up to the units that have been highlighted as problematic and solve issues on them directly instead of going through the building and looking at every single piece of equipment. This allows for maintenance of VRF systems in a very non-intrusive fashion. Furthermore, the benefits of connectivity, there's also the reliability impact, the comfort impact, and the energy impact. So maybe you have a ducted style indoor unit where the filter's not been cleaned. That's now going to have that impacts your comfort, your reliability, and your energy. Now we can look at that remotely, point that out as an issue, and then suggest some fixes for that. While I did mention 3 quarterly remote checks and 1 on-site check, we also have a multiple of hybrid options available that are very non-intrusive. As Scott mentioned, indoor environment quality is now a huge concern within the K through 12 environment. This also allows for additional monitoring of particulate matter, total VOC content, noise, and light. This has implications beyond just the health-related concerns that the pandemic has brought on. But if you want to learn more about it, you can go to www.trane.com/VRF. And with that, I think that is the end of the prepared content that we have, and we will move into the Q&A session.
Thank you all for that great presentation. And now our presenters will answer questions from you, the audience. Please type your questions for the presenters in the Ask a Question box on your screen, and we'll get to as many as time allows. Questions that we don't get to today will be posted online at www.csemag.com with the archived version of this webcast. To download a certificate of completion or a copy of this presentation, please use the Event Resources tab on the left side of your screen. All right, well, the first question goes to you, Mohammed. How often do you use an air source heat pump in northeastern cold climates?
So, all the time. I've used, mini splits for stores, all the way to large VRF systems for office buildings, and things like that. And not just, VRF systems, but VRF systems that are acting as the sole source of heat for that space without any backup. It's an increasing design choice that's being made in the Northeast. Brian can certainly speak to that a little bit more in terms of his experience.
Yeah. I mean, we're seeing it all the time. It just seems like that we always have the owner that just wants the heating and cooling from one device, and that's that. And none of that, and for cost perspective too. So I mean, now that the technology is there with these heat pumps, the VRF systems are able to operate at very low ambient temperatures. It just makes all the sense in the world. So I mean, we're seeing it, just in the last 5 years. I mean, we're seeing a huge increase for this type of technology and these type of systems.
All right, so let's see here. The next question, Mohammed, I'm going to send this one over to you. And we have some duplication here in the questions. So let me ask a couple of them together, and perhaps you can combine your answer. Are MERV 13 or higher filters available for the indoor units? And then talk a little bit about MERV 13 2-inch thick filters. Is that an option?
Yeah, so we have, as Scott mentioned, we have, ducted style indoor units, and we have ductless style of indoor units. On some cassettes, on the ductless side of the line, we now have MERV 13 available. But on our ducted units, we have a filter box option available, and that does provide 2-inch MERV 13 filtration across our line.
All right. Got it. All right, let's talk a little bit about air quality, DOAS, all that kind of stuff. Can you provide a little bit more information about that? I don't recall, Scott, is that you that talked about that? Could you go into a bit more detail?
Sure. Yeah, and I can see a couple questions in here around maintaining proper ventilation and filtration. I think Mohammed just hit the filtration piece, but what I would share is they play to each other. So if we're looking at, how do we ensure we've got code ventilation? Well, again, as we design these systems, we want to do, to the best of our ability, get the ventilation up to where code would be based on ASHRAE 62.1 ventilation rate. Our recommendation there is to follow the VRP method, ventilation rate procedure, although IAQP is an option if you want to do those calculations. The other thing I would want to stress here is there is a question around, the ability to go 100% outside air like you might do on a VAV system. I would draw attention to a tool that ASHRAE published early this year called the Equivalent Outdoor Air Calculator. What that tool allows us to do is to actually look at how we can look at air changes from outside air, but also how well are we cleaning the air that we're providing to the space, whether that's through a MERV 13 filter, a UV light, a portable HEPA, whatever technology that may be, to deliver on a cleaner space. All of that to say, the air does not have to come from outside for the space to get safer. We want to make sure we're providing code ventilation, but you don't have to overventilate if you can remove the pathogens and improve your indoor air quality through the use of filtration. So hopefully that answered about 3 of those that I can see that are up.
Yeah, there are quite a few questions. Thank you very much. Ryan, I'm going to send this next question over to you. Can you talk a little bit about reasons for suggesting electrically driven refrigerant heating versus standard gas?
Yeah, I think it's, I guess a lot of this is driven by the, owners' desires, but just all the, the climate that we're in right now is, everyone's trying to reduce their carbon footprint and trying to back away from fossil fuels. So, and also getting into more, green energy. So, so it seems like that, the industry is moving away from, just standard, gas consuming products and getting into more, electrically driven products to do your, building, heating, cooling. So I think that's, and that's what's driving it. And now that, more green energy is available. So I guess it's, it's to be more efficient and, reduce our carbon footprint. I mean, that's the main reason.
There are also, just to add to what Ryan said, there are also, decarbonization pledges that cities and companies have put out. So the city of Boston, for example, wants to be carbon neutral by 2050. And, every high rise that's going up in Boston, they want you to either be all electric up front, or they want you to have a plan to be all electric by 2030, I believe. And so increasingly, it's also a regulatory issue.
Correct. And the conversation seems like it always comes up during early design, where it's not always chosen to be all electric, but it's always talked about, and just the feasibility of it.
All right, this next question, Mohammed, is for you. This one's about controls. So let's say if a school already has a building automation system, how does the separate controller from a different system or from a trained system interact? How do you help that school staff understand the system and its relation? Can you talk a little bit about that integration?
Sure. So the Tracer SE, the controller, it's a BACnet capable device, and so it can integrate all of the points into an existing BAS as long as the existing BAS is capable of BACnet. Not only that, but it also enables points that were typically not accessible on a VRF system industry-wide, right? So it allows you to be able to look at maintenance data for the condensing unit, the refrigerant temperatures and pressures, and things like that, in order for the school staff to better understand how the VRF system is working. And then there's also proprietary analytics built into it that can be used to run reports to suggest corrective action is needed.
All right, got it. Thank you. Scott, a couple more questions for you. Let's talk about ventilation requirements. How do you handle varying ventilation requirements in conjunction with VRF in schools? If you use like energy recovery, is humidity of concern? Can you talk a little bit about that?
Sure. So when we're looking at the varying ventilation requirements, there's really a couple of different ways to do that. Many systems will be designed where anytime that you're occupied, you're providing that ventilation. As Ryan had mentioned, we want to look at space use to determine, are we matching this up? So as an example, would you want a DOAS unit connected to classrooms and to an administration area that are served by two separate VRF systems? My suggestion would be decouple those two, either as two different units, or potentially put in some form of a zoning system where you're not going to be over-ventilating an unoccupied space. So that's one thing to consider, is making sure you're only ventilating when you're occupied. We have seen a trend towards actually having more precise ventilation using a zone damper paired with the CO2 sensor so that we don't over-ventilate as an energy savings method. But again, that does add the cost of that additional damper and that CO2 sensor. Specific to humidity, when we're looking at humidity control, the recommendation from ASHRAE is where possible to maintain humidity below 60% and above 40%. Now they do put some exception in there for existing buildings that not every building's envelope is made for that. So in northern climates, if you're maintaining 40% humidity and it's very cold outdoors, you might not have the building envelope that's able to handle that. So that may not be something you're able to do. But the guidance is where possible to maintain between 40 and 60% RH.
All right, very good. Thank you. If you do have a question for one of our presenters, you can type your question in the Ask a Question box on your screen. We do have several questions. We will not get to all of them today, so questions will be answered in writing, either at www.csemag.com. That is the Consulting Specifying Engineer website, with the on-demand version of this event, or you'll be contacted directly by one of our presenters or their colleagues. If you'd like to download a certificate of completion or a copy of the presentation, please use the Event Resources tab on the left side of your screen. All right, Mohammed, next question goes to you. So let's talk about model numbers. Are VRF model numbers the same as Mitsubishi or other manufacturers?
Initially, when the joint venture happened, yes, Trane offices were providing VRF products with the same model numbers as the Mitsubishi model numbers. Since then, however, we've brought out Trane branded products in all of the various series of Mitsubishi equipment that were sold prior to the joint venture. The product is identical. The parts, the service tools, existing legacy install compatibility, backwards and frontwards, it's all the same. We have situations happen all the time where we have a Trane branded system, but we are putting a Mitsubishi branded indoor unit as a replacement on it. So yes, we do have Trane branded product, and it's primarily done as a branding effort.
Sure, got it. Thank you. Ryan, the next question is for you. A little bit more about fresh air. What are the pros and cons of ducting fresh air directly into the room versus directly to the return side of the VRF fan coil?
It's a very good question. Probably a long-winded answer. I'll try to shorten it up. It depends. I mean, it depends if you're conditioning your air. Typically with the VRF systems, we try to do 100% outdoor air units with an energy recovery device. So that means we're just putting the ventilation air needed into that space. Now, if you're heating and cooling it, depending on the season, depending on the temperature coming out of your outlets and your ductwork, I mean, you don't want to make your VRF system do extra work. So, I mean, a lot of the times we might do, space neutral. So if you're delivering it at, 75-degree air out of your ductwork, then you can put it directly into the space. Let's say if you were only heating the air. So in the summertime, you might have the air coming out of the unit at 80 degrees dry bulb. We don't necessarily recommend putting that directly into a space. You'd probably better off mixing it through the return of the VRF fan coil unit and then out to the space. But one thing I will caution everybody about is every coil manufacturer, whether it be a fan coil unit, VRF fan coil unit ventilator, whatever it happens to be, they have certain entering air coil conditions that you have to meet. For a 1-ton unit to be 1-ton capacity, or a 2-ton unit to be 2-ton capacity. I mean, generally it's 80 degree dry bulb and 67 wet bulb. So you just, depending on what you're doing and the air temperature coming out of your unit, you just have to be careful and talk to your local representative about a selection with that mixed entering air temperature, just to make sure that your fan coil unit is and you're getting the correct. Because if you could have a situation where, your air is, your mixed air temperature exceeds 80 degrees or is well below 80 degrees, and your nominal 2-ton unit is operating like 1.5 tons, and that could affect your loads and the temperature in the space. So I guess short answer, it depends, but we've seen it both and we've done it both ways.
Thanks, Ryan. Yes, it depends is definitely an answer. All right, so Mohammed, this last question is for you. Is there a VRF unit ventilator option?
Yeah, so we do have, Trane has made a unit ventilator for a long time. We do have a unit ventilator option that's compatible with the VRF condensing unit. It also has, there are control options to enable the hot water valves as well. And so that we are increasingly seeing schools move away from that hot water due to the electrification reasons that Ryan and I mentioned previously, but we still do support that.
Excellent. Well, thank you very much. Thank you for those great questions, and thank you to our terrific speakers, Mohammed Nassan, Ryan Flynn, and Scott Huffmaster, for sharing their time and expertise. I'd also like to extend a special thank you to our sponsor, Trane, for sponsoring today's event. And now that we're just about done, we want to hear how we did. The exit survey will pop up on your screen as soon as this webcast ends. Please take a moment to complete it because we use this information to improve our webcasts. Finally, on behalf of Consulting, Specifying Engineer, and CFE Media and Technology, I'd like to thank you for attending. This now concludes our webcast. Thank you and goodbye.